Something special for us today, and I put it in this box. So you don't need anything. I just want you to look at this box. I just want you to try to think about what's inside this box, and I'm going to give you a little bit of a description about what's inside of it so that you can imagine what's in there. You don't have to take notes on anything, but in this class, we talk a lot about physical things in the world. We talk a lot about technology. We try to be solution-oriented and forward-thinking people. And so I tried to bring something. You can feel it has some weight to it. There's actually something in this box, which we'll reveal here in a moment. But I brought this because what's inside of here, I really wanted to share with the class. It's something very special. So check out that box and try to visualize what you think is inside of this. You guys know about air pollution, which is a major problem that exists on our planet. It causes a lot of issues for our society, for ecosystems. What's inside of here has the capability of taking air pollution out of the air. It has the capability of cleaning the air. So it's a very useful tool. It's not just useful in the air. It can also move things around, and it can remove pollutants out of the ground, which is pretty cool. Another big problem in our world is the amount of energy. You hear about energy security, energy availability. We talk about fuel and electricity and fuel efficiency and cars and all of these things. Everything on our planet needs energy. This is also capable of storing energy, holding energy, producing energy. So it's useful in that manner as well. There are a number of other things that are interesting about this, but does anyone want to take a stab at what's inside the box? Yeah. A plant. Should we look? Any other guesses? This gang, look at this. Everybody look at this. This, by the way, is a very lame demonstration. It's corny, it's cheesy. I totally get it. But if you don't learn anything in this class, please leave this class and be amazed by what happens on this planet. This is an incredible thing. We're going to talk about this a little bit today and explore it. But what we want you to try to understand and get is more than just all the terms and the definitions. You should be amazed by what occurs. You would never be here. Nothing else would be here. You walk by this plant all the time. Does anybody know where I got this plant from? Outside STEM. They're just over here by the Herman Plaza. Very good. But you probably walk by this all the time and you are not amazed by it, but you should be. Because this is incredible. In fact, this is the most important and amazing mechanism and thing that exists on planet Earth. And I will fight anybody who tries to tell me different because I'm a plant guy. But this is incredible. Let's look at a little bit about why it's incredible and talk about it. But as part of our process and our learning, I want you to be amazed a little bit about what we're seeing. On the first day of our class this year, I showed this slide on the very first intro of our class. And this is a beautiful picture taken by NASA of our Earth. And it has color, and it has vibrancy, and it has living things. And it's because of this process. For many millions of years, this process wasn't occurring, and our planet looked a little bit what this looks like. This is an artist rendering that took place by NASA and this project to put together what our Earth would look like. It would look like what it looked like in the very early days. Extremely hostile. No availability for living things to exist. There's no oxygen in the air. It's being bombarded by caustic chemicals that are coming out from underneath the core of the Earth, volcanic eruptions, sulfur, clouds, all of these things. This is what it would look like, much more similar to Venus than what we have instead. So if you don't think plants are amazing, welcome to your new planet. All right, let's get into our work here a little bit. I wanted to stop and pause just very briefly on this. This is the narrative of the class. that we're exploring, and it makes sense to take a pause because we're transitioning through this narrative, this story that we're telling on the syllabus. It exists right underneath the picture, so we're not really following a unit. We're following this story. It's a 100-word abstract. And here's the first sentence, which we've completed now. And it's everything on Earth is highly interconnected with numerous natural systems that vary across space and time. We're done with that now. So here's my question, and this is kind of a rhetorical question, but I want to think about it, is what are those systems? Let's answer that part out loud. What are some of the natural systems? Yeah. We got the rock cycle. Fabulous. What else?
Water cycle.
The water cycle. There's a whole lot going on with climate and weather. What else?
The phosphorus cycle.
Phosphorus, which is interestingly sits inside of the rock cycle, but I really like that because phosphorus is key. We'll see that here more in Module 7 in our next time. What else? There's another key one that the phosphorus cycle is also kind of nested in.
Carbon cycle.
Carbon cycle is nested inside of this one as well. Very good. There's one, like we were looking at this kind of more macro or a little bit bigger than the carbon cycle or those. Think on par with like the rock cycle. We just spent a lot of time on it. Soil formation. And then we have these geological processes. He's said plate tectonics down here, which is key in both soil formation and rock formation. So the second question is are any of them more or less important than one another? This question would be fiercely argued, and it usually breaks down by discipline lines. So a geologist would maybe try to say, well, the rock cycle is key. Without the rock cycle, you wouldn't be able to have the parent material necessary. There would be no soil cycle or soil formation without the rock cycle. So they would say this is key because it produces life. Without the rock cycle, you can have no life on the planet. But a climatologist will look at it and say, that's wrong. The climate cycle is much more important because it's the availability of water and precipitation. That's the key thing. Without that, you could never have life. Or a soil scientist or an agronomist would look at it and say, yeah, but the rock cycle is nothing without the formation of soil and the cycling of nutrients and all of these things, because that's what produces life. The key thing that all of those people, even though they're arguing about which cycle is the most important, they're all pointed at life. The measuring stick for the importance of the cycle is how critical is it in producing life on this planet. Life is the key thing. As far as we know, there isn't life on any other planets. There's no life on Mars, Venus, and we've been exploring the universe. So far, we haven't found anything else. The rock cycle on Jupiter, it doesn't happen to be that important. We don't care about it that much because it doesn't produce life. So when we're thinking about these cycles that we've now explored, we're going to start looking at, well, how do they connect to life? And this is the second statement of the narrative. It says, living organisms require both energy and resources, and therefore conversions of energy and matter underlie all ecological processes. This doesn't mean very much yet to you, but hopefully it will mean a little more by the end of today, and increasingly so as we continue our exploration of this class. The biosphere, which is this new word that's going to come up as part of our work right here. Bio, it comes from the Greek word, the root for life. So the classical study of biology is the study of all living things. It has that same prefix part of the root word there. So the biosphere, when we've seen sphere before, how have we been talking about it? What does it mean? By saying, what are some of the other spheres that we've explored? The atmosphere is one. The lithosphere is another. So when you hear the word sphere, we're talking about this space where, like the atmosphere, where these air particles, or the geosphere or lithosphere, where earth things are. So the biosphere is all living things. All the living things are part of the biosphere. If we were looking at the biosphere in an ecosystem, what we're talking about is the living things. Fabulous. Let's keep going. Here's the learning objectives for today. So all that was a little meta, but this is what we're going to explore today. We're going to be looking at the boundaries of ecosystems a little bit. We're going to be talking about how resources, specifically energy, most critically, but a little bit about some of the matter, how do those flow through the ecosystems, And then we're going to look at productivity within ecosystems, which lays on top of, well, how does all of this energy move back and forth? And that's the trophic levels. So we'll explore all. This has a lot of learning targets for today because it's kind of complex. I love this picture. This was Photo of the Year, National Geographic in 2015. It's a perfect picture of a food chain. Alligator eating a big fish that's eating a smaller fish. That is a beautiful food chain, agreed? Here we go. Let's start out with where we've been. So these questions I want to consider and pull out. So the Earth, just to keep it all oriented, is this a closed system or an open system in terms of energy? It's an open system. And in terms of matter, lots of matter going in and out, or no? It's closed. And so energy, why is it open? Where is the energy coming in from? The sun. The picture is a great revealing answer right there, isn't it? And what form? So the second question here is what form? So how is that energy moving from the sun to earth? Like what format of energy and what kind of energy specifically are we talking about? We have radiation as the format of the energy. And what's actually flowing, solar radiation, what's actually coming towards the earth? It's not quite heat. Heat, it comes from, these things go into the earth, and then conduction, so that's where the heat, it's the release. It's the light, and it has a specific name. I just want to pull it out because I can come back to it later in our class, so I want to keep it fresh. Somebody, who was saying it? Yeah. Photons, oh great. Photons. I just couldn't hear you, I'm sorry. So here's where we go today. This picture, it's accurate for the most part, but it has some problems. I have some issues with it, and so we're going to look at those issues. But this is the level that we want you to understand of these processes, and so we're going to look at it a little bit, and it's this exchange of things that are happening. So we see a little bit of energy flow, but we also see it flowing across. There's this piece where matter is related. So it's photosynthesis and cell respiration. And we'll come back to that in a second. But I just want to show, and there's a lot going on this graphic, and this is kind of like a little forecasting. If you ever study science at any level beyond what you're studying now, you'll have to get very familiar with this. This is the key. It underpins everything that happens in biology in terms of the amount of energy that flows and how energy flows and how things exist within organisms. And so this shows, this is from a graphic, this is from a publication that I helped work on in 2016, and that's not a, oh, look at me kind of thing. What I'm trying to show here is that this science is still fairly new. We're exploring and we're understanding the nuance of photosynthesis at increasing levels more and more. So this is a hot topic. It's a very dynamic field inside of the biological field. So the graph and all this you don't really have to pay attention to, but I wanted to show what this cycle looks like in its full complexity of movement of things going on. But what I want to focus on for our level, the things that you're responsible for, is what's in green text here at the bottom. So photo, if we want to break down this word, it comes from the Greek word phos, and that refers to light. So we're talking about light, and then synthesis, whenever you hear that word, you know it means we're putting things together. So in this case, we're using light to put things together. And so photosynthesis, what I need you to have right on the tip of your mind when you hear the word photosynthesis is what we're doing is we're converting light energy into chemical energy. From light energy into chemical energy. When I say chemical energy, what am I talking about? What is chemical energy? It's potential energy, but how does it reside? What is its form? What does it look like? So it could be the food, and so you eat food so that you can capitalize on this energy. So when you have a piece of pizza or a burger or whatever, or a piece of celery, whatever you're going to eat, it has chemical energy. Why does it have chemical energy? Where is the energy inside of that? The nutrients is the matter part, so keep that in your mind because we will talk about that at great length. Yeah? Carbon is a big part of it, and it can be a big piece. Glucose, which has the carbon, and so these sugars. What is it about sugar? And carbohydrates is a bunch of sugars.
Big complex molecules.
Big complex molecules. What do they have? Why does aluminum nitrate not have energy, but glucose does? Well, actually, hold on. Erase that from your mind. Let me go back. When we did our lab and we put chemicals in a bag and we did a chemical reaction and we felt energy, transfer of energy, why did that take place? There's this thing about bonds. So the bonds between elements, that's where the energy comes from. So what we're doing when we say this photosynthetic process, what we're talking about is we're taking light energy and we're using that to create bond energy. So the food has energy because it has chemical bonds inside of it. Chemical bonds that are available. All right, great. Here's the second part, and this, again, is needlessly complex for our purposes, but I feel a deep obligation to show you what the whole thing looks like so we can think about a few things. But this is a mitochondria, which is an organelle inside of a cell. So this tan, jelly-like thing is a mitochondria. That's where this process takes place. So the process that we're talking about is cell respiration, and there are a bunch of enzymes and a whole lot of things happening here. But what I want you to know is what's occurring is there's an input coming in, and what it allows you to do is create adenosine triphosphate from adenosine diphosphate. And so just going back and forth, breaking that bond and releasing the phosphate or bringing it on, that's where all of the energy that does everything that organisms do for growth, for movement, all of that comes from that process. And so the two key inputs, they actually come from the outputs of photosynthesis. So let's go back to our easy model here. So we looked at the complex model so we could see the full thing, and it's a little overwhelming, so let's look at the simple one again. So here's photosynthesis. We have light energy, and we're using that to create chemical energy. So we're doing something, we're creating new bonds, new molecules together. Here are the inputs. And let's think about where do these inputs come from? And by where, I mean what sphere. So carbon dioxide, what sphere does that come from? The atmosphere, right? It's out in the air. And then when it goes into the plant, what sphere is it in? The biosphere. It's part of the living things now. And so that's one of the inputs. The second one, water. Where does that come from? It's one of our natural systems, by the way, that we've studied. Sentence one of the narrative. Where does the water come from? In the environment. Just like some giant with a big watering can, right? Exactly. What sphere does the water come from? I heard it. Atmosphere, right? So precipitation occurring, and then the plants just take it in out of the atmosphere, or no? They take it from the ground, so it goes to the geosphere or the lithosphere, and then it goes into plants, and once it's in plants, then where is it? In the biosphere. So keep track of the inputs, but keep track of where they're going and where they're coming from and going to. So carbon dioxide and water through their respective spheres into the plant. So one of the things I don't really like about this picture is it just shows you this leaf, but the water actually comes in through the roots. It doesn't go through the leaf. But that's just a little bit of plant nuance for us. But it comes together, so we use the sun energy, and then we create new molecules. So now we have chemical energy stored in this form, which is glucose. And then one of the other byproducts is oxygen. Those are the two critical inputs for cell respiration. So here shows an organism that's eating a plant, so it's consuming the sugar that's stored inside of the plant, and it's breathing in oxygen. And so those are the two critical inputs that it needs to create adenosine triphosphate and displace that, moving those phosphates back and forth. That's where the energy comes from for growth and movement, etc. And then here are the outputs here. So energy, that's key. That's what we're after. That's why we eat. That's why the mouse eats. That's why cell respiration takes place. But they expel carbon dioxide. So it's gone from what sphere to what sphere? If it's in the mouse, what sphere is it? And where does it go? Into the atmosphere. And then we have water being produced as part of this as well, which a lot of it is stored in the organism, but some of it goes out as a waste product. So it goes from the biosphere out into usually the geosphere. It goes on the ground as a waste product. But one of the things I don't like about this picture, and it's really key to have in our mind, is whenever we have transformations in energy, we have the laws of thermodynamics at play. And the second law of thermodynamics tells us that there's going to be, as energy transformations take place, the energy quality is going to be decreased as those transformations take place. So heat is lost. So in this process, heat comes out. Keep that in your mind. Let's keep going on. And what I want to pause here while we're looking at this is I want to make sure the problem that I have, even though this is the proper level, is there's some misconceptions, and I want to make sure we get those cleared up in our mind because they're critically important to understand. The first one is, sometimes I hear this, that plants get their energy from the sun. That's kind of true. Plants use the sun's energy to make the energy that they use. So plants also undergo cell respiration, so they consume sugar. They're not using the sun's energy directly. They're using it to make chemical energy in the form of sugar, and then they're using that, which is the second misconception. They go together. That plants don't undergo cell respiration. They do. That's how plants get their energy for growth and all of the processes that they need to do, all the biochemical processes that they undergo. Comes from cell respiration just like it does for you and I. Plants undergo cell respiration. They don't get the energy directly from the sun. The last one is that plants only expel oxygen. We know that's a byproduct of photosynthesis because of the processes that we've showed, but they also expel CO2 because CO2 comes from cell respiration. So this process doesn't need animals to go in the cyclical fashion. All of this that happens in cell respiration also happens in the mitochondria of plants as well. Does everybody feel good about that? That's going to be key for the next thing that we're going to look at here. The photosynthesis piece and the definitions are there on the right, but just ignore those for one moment because I want to show this piece on the left. Even though I introduced it as this beautifully amazing thing that has changed and transformed our planet in a bunch of important ways, which is photosynthesis, unfortunately, the process kind of sucks. It's very inefficient. So 99% of the energy that flows from the sun doesn't get absorbed by plants and get turned into chemical energy, only 1%. Imagine if we could capture more of it, that would be outstanding. But the plants, the solar energy, they're only able, across our planet, a global average is about 1% of the total energy that comes to the planet. The other 90%, 99, goes into heat through conduction, and that powers climate and weather, which is a lot of energy. So per those misconceptions, and keeping track of what's going on with plants, the plants use that and create chemical energy, but then they undergo cell respiration. So the total amount of energy that's taken in and converted into sugars by plants is called the gross primary productivity. So the gross part, just to focus on to begin with, means the total. It's the total amount that the plants are able to convert. But then they use some of that energy, and so not all of it is available for mouse or deer or us. So some of the energy is consumed by the plants and used by the plants as part of their cell respiration. So the available is the net, so we know that from algebra what the net means. So the net primary productivity is what is the leftover amount of energy that's available. And that leftover amount of energy is going to power everything within the ecosystem. Does everybody feel okay with this? All right. Good. So here's a couple key terms, and then we're going to do a quick exercise right after this. But I want to get these terms in our mind a little bit. Trophic levels. So this word troph, it actually has a Latin root, but it means food. And the trophic level, what we're talking about is levels of a food chain, which I know you guys have heard about that before. So this eats that, then that eats something else, and so on and so forth. If we follow that just in one linear direction, that's called a food chain. But we know in an actual ecosystem, things are relatively complex. So one organism doesn't just eat one thing, it probably eats several, and it might get consumed by several different things. So if we put that whole picture together, that makes a food web, and the trophic levels are where you're at on those webs. So let's get into the trophic levels just a little bit here and show what things look like. So every living thing is an organism, exists in the biosphere, and we can divide those into two categories. So here's this word again, troph, and auto, which you know. So anything that produces its own energy, it makes the energy and then uses that energy in cell respiration, that is known as a producer or an autotroph. Those two things are synonymous. So we have things like plants, algae, and then certain selected bacteria. This for sure is not a comprehensive list, but it shows you what some of those things are. So the producers, those are at the bottom. So on that previous slide, we looked at these key terms, gross primary productivity. So the producers, that productivity part, that's where those two things are joined together, and these are the organisms that make their food. Then we have a whole bunch of organisms that eat that food. So consumers, heterotrophs, meaning they take in food from different forms, and then the troph again is there as food. And so we have all kinds of levels. This also is not an exhaustive list, and I don't want to go over the whole list because I think you guys know some of these terms already. These are not new terms for you, and they're also in the textbook, but I just wanted to show you what these layers look like. So here's what I want you to do. I'm going to show a really short part of a film, which is an awesome documentary done by the BBC called The Hunt. And we're going to look at some things. And what I want you to do is list the organisms that you see, and then also just notate the relative abundance of those organisms. And then we're going to produce a food chain as part of it. And it's kind of a simple exercise. And we'll just watch the film together. If I can get my mouse over here.
Leopards are the most versatile of all the big cats, adept at finding cover in the most unpromising places. The steep walls of the gully are now her cover for an ambush. The male puku is close enough, but he's too big to tackle. She needs to slip past him without being seen. If he spots her, he'll blow her cover. Slowly does it. To succeed here, she needs to find prey grazing close to the edge, or better still, in the gully itself.
I felt like I couldn't show a full thing where an animal would get killed in front of everybody. So, but you can still imagine what's going to happen in the remaining 2 minutes, okay? We don't have time. All right, so just give me what some of the organisms are really quickly that you saw, because I want to keep track of this and pull out a key concept here. What are some of the things you saw? There's obvious things and there's some more subtle ones. We see the leopard. We see the impala, the hoofed animal there, yep. What else? There's a bunch of plant growth, there's grasses, there's trees, there's shrubs, there's all kinds of things there. So you can think about how those go into a food web, which is pretty simple, but keep that in your mind because we're going to look at this here. And so the trophic levels is the term that applies to, well, we want to figure out, well, where do these exist in the food chain? What level do they make up? So the producers are at the bottom because those are the ones that take the sun's energy and convert it into the chemical energy. That's what makes any energy available in the ecosystem to begin with for things like primary consumers. So the things that are the first ones, primary to eat, the producers, consumers, eating primary producers here. Things like the zebra or the impala would be the example from the film. And then after that, there's energy available for a predator, and this could go up to the secondary level, the tertiary, quaternary. For most of our applications, we're going to think about it maybe up to the tertiary level, which is 3 levels of consumers plus the primary producers. So this key term at the bottom in green here, energy efficiency, tells you, well, how much is available? So we know per thermodynamics and energy transformation, there's losses to heat all along the way. So we're losing energy, and this is what it looks like. And you can use in your mind as a general rule of thumb, this isn't a perfect number, but it's about 10%. So the losses are actually quite severe. You start out, if the total amount of energy here, we have 99% of it can't even be captured by plants, then the gross primary productivity is a large number, but then plants use some of that for cell respiration, and so the net primary productivity is the number that's shown here in the green box. That's how much is available, the energy content inside of the grass, and only 10% of that can be used by the next level, and then 10% of that number by the level after that. So we call this thing the rule of 10, and so you can think about the amount of energy that's available through the trophic levels. So if you want to have energy available for tertiary, quaternary consumers at the top, what do you have to have? In order to have enough energy way up here for something like a lion, what do you need? You need a lot of producers and you need a lot of energy right here. Excellent. All right, we're going to do one more exercise to round out our time here. So let me go to the next slide, and we're going to do a little bit of practical work looking at this together. So I have 3 questions here, and I keep getting questions from students. They say, man, the tests are really hard. The strategic analysis is really tough. And it's because you haven't practiced this kind of work enough. So we're going to continue to stitch it into lectures and our daily work in the labs. So every individual should attempt these 3 questions. They're actually fairly difficult questions. The first one has a typo, by the way. So I'm saying this information around the formula for gross primary productivity, but that should be kg for kilograms, not kb. And that means the plants produce a lot of mass, but we don't care about all of that mass. We just want to know how much of that mass has energy content. So that's the kilograms of calories per meter squared per year. So that one should get you there. And then the second one is using information from your knowledge about the natural systems of climate and weather to assign latitudes relative to here. And then this is looking at the rule of 10 or the trophic levels. But I've given you specific numbers here, not just 10%. So figuring out how much energy is available at all of the respective trophic levels. We'll go here. We have a little bit of time, and we'll touch base at the end of class together in a large group. So everybody attempt these 3 questions.